Alrighty, let's take a look at page 93. So we're going to start our next section today. Still looking at graphs. This whole first unit is a very graphical analysis unit. Okay, we've been looking at above x-axis, below x-axis. Where's a graph increasing, decreasing, constant? Where are specific points located? Can we graph piecewise functions? We looked at absolute value piecewise functions in the last unit. A lot of graphing things. In this section, we're going to focus on a different graphical characteristic, specifically symmetry. And I think you've heard that word before. Symmetry is like looking for a pattern or some type of connection on the graph that we can maybe fold or rotate, not to get too far ahead of ourselves, the graph to develop some type of picture. Now, in geometry, I think you guys focused on two different types of symmetry. I hope these words sound familiar. They are reflective or rotational. Kind of sound familiar? Maybe, maybe not. Okay? What we're going to do is we're going to define what each type of symmetry represents, and we're going to take a look at how we can classify the four graphs at the bottom. Okay? So, in terms of reflective symmetry, we're looking for how we can fold the graph. In other words, can we fold it in a particular way so that one side of the graph would match up with the other side? So for our definition, we'll say a graph has reflective symmetry if it can be folded over an imaginary line to match up with itself. So reflective symmetry is all about folding. Rotational, on the other hand, for the lack of a better word, is about rotating the graph. So for our definition here, we're going to say we have rotational symmetry if you can rotate a graph 180 degrees, basically half a circle or upside down. And if that upside down graph looks exactly the same as the original, it's said to have rotational symmetry. So rotational symmetry is if it can be rotated 180 degrees, aka upside down, and produce the same graph. Okay, so with these two definitions, we're going to take a look at the four graphs on the rest of the page and try to classify. Do they have rotational? Do they have reflective? Maybe if they have reflective, okay, that folding idea, we can determine where that imaginary line is located. So let's see how we can tackle these. So look at the first one here. Can you imagine folding that graph somehow? Okay, just folding it once and having maybe the left side match up with the right side. If you can't think about folding it, can you rotate it upside down and it would produce the same graph? Okay, what type of symmetry do you think that this graph might be classified as having? Yeah. Rotational. Okay, so maybe if you want to try to take the paper out of your binder or folder, okay, take a good look at what the graph looks like normally. And if you were to flip it upside down, isn't it the same graph? Okay, exactly. So that's rotational. You can flip the graph upside down and it would be exactly the same. So this rotational symmetry kind of has a specific other name you might hear it referred to as. It's called sometimes origin symmetry. And the reason it's called that is because if you could imagine putting your finger on the origin and rotating the graph that way. You see how I did that? I just put my pointer on the origin and rotated the paper. You see how it would produce the same graph? Okay, so origin symmetry is when the origin stays still. Okay, you put your finger or thumbtack there and you just rotate the rest of the graph and it would produce the same picture. Okay, so that's origin symmetry. What about the graph on the right? Could you imagine rotating that one and getting the same graph? Or can you fold it somehow and it would match up on itself? Can we classify it as either reflective or rotational? One of our two different types? Yeah.
Reflective.
Reflective. Okay, so if you're telling me it's reflective symmetry, can we determine where that imaginary line is? If you were to fold the graph, where would the crease happen to get one side to match up with the other? Can you look at it and think about it? How would you have to fold it? What do you think, Mario?
Y-axis.
The y-axis. Okay, so if you took the left side, folded it over, made a crease on the y-axis, this left-hand side would match up on the right-hand side. So we'll say that not only is this reflective symmetry, but it's specifically y-axis symmetry. That's where the imaginary line or crease is located. All right, let's check out the ones at the bottom. What about the bottom left one? Could you put your finger on the origin and rotate your paper and you'd get the exact same graph? Or is there some way you can fold it and have one graph match up with the other one? What do you see, Mario? Ooh, okay, so you're giving me the equation, which means this is reflective. Okay, so the equation of y equals x is a slanted line going through the origin. So imagine like folding the graph corner to corner. If you took this top left-hand side and folded it down to the bottom right, the crease would be that diagonal, which is the y equals x line. And notice how if you did that, the graph on top would line up with the graph on the bottom. Can we visualize that? Sometimes that one's a little hard to see. Okay. What about the last one? Can you rotate it? Can you fold it? What type of symmetry? Good, Kyle?
Reflective.
Reflective. And where would that crease happen? The x-axis. So if you folded it across the x-axis, the top half would line up with the bottom half. Good. Are we okay with those two different types of symmetry? Okay, you have reflective, which is the folding, and notice how you might have different locations where that fold happens. You have the y-axis, you have that diagonal, or you have the x-axis. Rotational is just that rotating 180 degrees. That's kind of the only option. Okay, so what we're going to do is we're going to investigate these 4 different types of symmetry a little further, and we're going to analyze different characteristics, different ways to identify or describe how we know a graph has a particular type of symmetry. I mean, I know we just did it based off the graph, but what if we're not given a graph? What if we're given a table of values, or what if we're given an equation? How can we still determine if it has a specific type of symmetry? So we're going to take a look at those different aspects. So this first one, we already know graphically what's happening. We said that this one was the rotational one. You have that origin symmetry. So if we were to describe graphically how we know this graph has origin symmetry, we can say it can be rotated 180 degrees to produce the same graph. We're going to take a look at something else though, but that was our basic definition of rotational symmetry. You can flip it upside down and it would be exactly the same. Let me ask you this. If you were to just focus on this first quadrant piece and you were to rotate it 180 degrees, a half a circle, where would this first quadrant piece land? What other quadrant? Yeah. The third. Okay, so if you have a quadrant 1 graph and you rotate it 180 degrees, it would land in quadrant 3. Very similarly, if you start with a graph in quadrant 2 and you rotate it 180 degrees, it would land in quadrant 4. So it's kind of the opposite corners, okay, opposite quadrants. Okay, so that's graphically if you have a picture. Let's say numerically we had some number values or point values. How could we determine if they had origin symmetry? So for numerically, we're going to focus on the ordered pairs on the graph. And what I want you to do is go ahead and write down those ordered pairs. We're going to try to find a connection between some of these points. Alright, so after you label those ordered pairs, can you find a connection or relationship between some of those numbers? You see a pattern, perhaps? Anything interesting going on? What do you think, Kyle?
Each ordered pair has a set that goes with it that is the opposite.
Okay, so each ordered pair, for instance, if I choose this one right here, has a set or another ordered pair that's related to it, and you said specifically the opposite. So if I look at this random point, -4, -3, notice how it has a corresponding point up here that's +4, +3. Do you see that? For instance, if I choose this random point, 2, 2, it has another related point, -2, -2. It's exactly the opposite. So numerically, we're going to say if the point x comma y, okay, a generic point, any point you want to pick. If the point x comma y is on the graph, so is, okay, we said that there would be an opposite point related to it. So what do you think that point would look like? Yeah. -x, -y. Good. Okay, so if we are given a graph, we should be able to rotate it 180 degrees to check out if it has origin symmetry. If we're given some point values, we could analyze if we have a regular point and an opposite point. That would indicate origin symmetry. Analytically, okay, by hand is kind of if we have an equation. Okay, how can we determine if an equation has origin symmetry or not? So this one's a little different because we don't have an equation up here. We will eventually get to those later today, but we're going to say that with this special point right here, if we were to substitute that point in, okay, so the substitution of the point -x, -y. If we were to plug in that opposite point into the equation, and maybe did a little simplifying, if we got out the same original equation, then we just confirmed it has origin symmetry. Okay, so the substitution of this point would produce the same original equation. Okay, I know we don't have an example of that just yet, but we will get to those by the end of today. Okay, so we'll come back and reference that analytical definition. Okay, so those are certain things we can look for origin symmetry. We're going to go through the other three options as well. Okay, let's check out y-axis. So graphically speaking, we said y-axis reflective symmetry was when we could fold the graph across the y-axis. So we can fold the graph over the y-axis, and it would, we'll say, match up. All right, let's take a look at some numbers, or maybe the ordered pairs. Let's see, -4, 1, -2, -1, 0, -3, 2, -1, 4, 1. Can we find a connection between some of those numbers or ordered pairs? Let's see, if the point x, y is on the graph, so is what other point? Can we find a connection? If you were to pick one of these random points, what would the related point look like? What's our connection or relationship? Can you find one? What do you think, Addison? Then x is flip, right? Changes sign, but the y stays the same. So for instance, if you were to pick the point -4, 1 and fold it over the y-axis, this is what the related point would look like, 4, 1. So the x changes sign, but the y stays the same. Perfect. So we're going to take this special relationship and substitute that into the equation, okay, if we had one analytically. So we'll say the substitution of the point -x, y would produce the same original equation. Can we see all these connections? Am I going too fast? It's making sense, I'm hoping. Okay, let's go ahead and check out some of the other ones. We had the diagonal symmetry, that was the y equals x, and then we had the x-axis symmetry. All right, so graphically, we said that we can fold the graph diagonally. Okay, so that y equals x line is a diagonal line going from opposite corner to opposite corner. And if we folded it diagonally, the graphs would match up. All right, what about some of the points? Let's pick a random point. Maybe this left-handed one. So that ordered pair would be -4, 1. If you were to take that point and fold it diagonally over that y equals x line, it would land right here. And that point has the ordered pair 1, -4. So what's our numeric relationship or connection? What do you think? Yeah.
X comma negative y.
Close. What can you describe in words what's happening? Maybe instead of going straight there, can you tell me in words what's happening?
The points are flipping.
The points are flipped. So if x comma y is the original point and you flip them, that would be y comma x. You see that? Okay, so nothing's becoming negative. Nothing is switching sign. You're just switching the order. Okay, so algebraically, we can substitute y comma x. And if we get the same original equation, we know it has this reflective y equals x symmetry. So this would produce the same original equation. All right, last but not least, x-axis symmetry. Graphically, we said you can fold the graph over the x-axis to match up. Okay, the top half would land on the bottom half or vice versa, however you want to fold it. What about numerically? If you were to pick any random point, where would the related point be after you fold it? Maybe we'll pick a pair to check out here. Can you find a connection between those two ordered pairs? What do you think, Kyle?
X negative y.
All right, so notice how the x value stays the same, but if you were to fold one of those points to the other side, the y value would switch, okay, become the opposite. So we would have x negative y. Perfect. So if we had an equation, which we're going to get to fairly shortly, the substitution, okay, plugging in that special point, would produce the same original equation. Okay, so I think graphically all these make sense. You guys can visually see the folding. I think numerically the points make sense. Okay, we are looking for those specific relationships between any original point you pick and what the new related point would be, okay, based off of that relationship. Analytically, it can be a little difficult because we have some plugging in to do, some simplifying. That's where some things can go wrong. So what we're going to do is practice these analytical ones on the back page. Okay, without a graph, without ordered pairs, how could we determine what type of symmetry these equations have? Okay, if we were to graph these equations, would we be able to fold them or rotate them in a specific way? So we're going to check all four types for each one of these. We're going to see how we could fold it or how we could rotate it. So let's go ahead and check maybe origin first. Okay. In terms of the ordered pairs, what was the special relationship for origin symmetry? If you were to pick any random point on the graph, what would the origin related point look like? Go ahead, Kyle.
Negative x, negative y.
They both would be opposite. Okay, so what we're going to do is we're going to substitute in negative x for the original x that's in there, and we're going to substitute in negative y for the original y that's in there. and we're going to simplify our equation. Okay, if you thought about negative x squared, negative x times negative x, what would you get? Negative times negative is positive. X times x. Good, Carl? X squared. So this would simplify to an x squared. Very similarly, if you did negative y squared, that would simplify to just y squared. Okay, we're not really changing any numbers in this case. We're just simplifying the variables. So if you take a look at your simplified version versus the original equation, are they exactly the same? Yes. Okay, so this equation, if you were to graph it, has origin symmetry. You would be able to rotate it upside down and the graph would be exactly the same. We don't know what the graph looks like, but we know it has that characteristic to it. Okay, because we substituted in that special point and we got out the exact same equation. Okay, let's go ahead and check out, what was our next one we did? Y-axis. What was the special point related to y-axis symmetry? If you were to pick any random point, what would the related symmetric point look like? Yeah.
Negative xy.
Negative xy. Okay, so only the x is changing, not the y. So we're only going to plug in negative x into that equation for x. So if we plug in negative x squared would be positive x squared. Do you get out the same equation? Yes. So not only does this graph, whatever it looks like, have origin symmetry that you can rotate it, but it also has y-axis symmetry. You can fold it across the y-axis, make that crease, and the left side would match up with the right. Okay, so it has two different types of symmetry. Let's check out the diagonal symmetry. Y equals x. What did that special point look like? If you were to pick any random point, what would the related symmetric point look like? What do you think, Kyle? This is the flipped one. Yep. They switch sides. Okay? So in terms of our substitution, we need to switch the variables. Instead of having x squared there, we're going to have y squared. And instead of having 2y squared, we're going to have 2x squared. Okay, you flip the values, just like that ordered pair is representing. So take a look at that simplified equation. Is that exactly the same as the one you started with? No. Okay, so it does not have that diagonal symmetry to it. All right, and our last one was x-axis. What did the special point look like for that type of symmetry? Good, Kyle?
X negative 1.
All right, so just the y changes. So in the equation, we'll keep the x squared, but we have to substitute in a negative y. And if we were to simplify, negative y squared ends up being a positive y squared. Is it the exact same equation? I think so. All right, so even though we don't have a picture, okay, a graph to look at, we know we would be able to rotate it 180 degrees and it would be exactly the same. You can also fold it across the y-axis and the x-axis and it would still be the same. All right, so maybe you can start to think about what this graph might look like. Okay, maybe not. Okay, but at least we have those different types of characteristics known about this particular graph. Are we doing okay with that? That analytical analysis? Okay, let's go ahead and try number 2. Origin symmetry. So the special point related there is that they're both opposite. Do you guys want to try this one on your own? You want to try all 4 of them? Give them a shot? I'll do them up here on the board so you can check them out as we go, but you guys go ahead and see how you can do. How'd you do? Pretty good? No, 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 yes? Yes? Okay. All right. No, 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 no. All right, let's check out 3. We're going to step it up a bit. We're going to throw it in absolute value. Don't let it scare us, okay? We're just going to simplify it just like all the other ones. Let's check out origin symmetry. That's where both values are opposite. So let's plug in negative x and negative y to see what's going to happen. Negative x squared, we already saw that was a positive x squared. What if you took the absolute value of negative y? Yeah. It would equal a positive y, right? So technically, taking the absolute value of negative y and taking the absolute value of positive y are exactly the same thing. Do you get the same exact equation? Yep. So we should be able to rotate this graph, whatever it looks like, and it would be exactly the same, upside down as it is right side up. Let's go ahead and check out y-axis. So this is when the x changes sign. So we're just going to switch the x value in the equation. Negative x squared, though, happens to be, or simplified, a positive. So it looks like we get the same equation again. So not only can we flip it upside down and it would be exactly the same, but we can fold it left and right across the y-axis and it would match up on itself. What about the diagonal, where the values switch? Do you get the same exact equation? Nope. Okay, so no diagonal folding going on. And x-axis, this is where the y value changes. All right, and I think we already said that the absolute value of negative y would result in the same thing as the absolute value of positive y. So it looks like we have x-axis symmetry too. We doing okay? All right. I want you guys to try the last one. All four. All right, so I think we don't really have a problem with origin, y-axis, and x-axis. So we get yes for all those. All right, I'm curious what you guys said about the diagonal symmetry. Did you get the same exact equation out? Yes. Okay, I know they're switched, right? But order doesn't matter when you add. Okay, so it is the same exact one, even though it looks a little different. So this is still yes. So this graph, whatever it looks like, you can flip it upside down and it's exactly the same, and you can fold it these three different ways and it would be exactly the same. Can you think about what type of graph that might be? Rationals or fractions? We don't necessarily have a fraction there. It's a circle. Not sure if you recognize the equation or not. Okay, this is a circle graph. Can you guys identify what the radius is? 5. Okay. Where's the center of that circle? At the origin. Good job. Okay. That happens to be a circle with a radius of 5. Okay, the square root of that number. And it's centered at the origin. Perfect. Hopefully that makes sense then. If you can picture that in your head, a circle, you should be able to rotate it and fold it a lot of different ways and it would line up on itself. We doing okay? All right, that's it for this section. Really quick, okay, but we're going to expand on it tomorrow, all right? You could probably start your homework, okay, really quick on page 97. Very similar equations to what we did today. And on the back, those are some thinkers I gave you.